probably live, huh? Let's see. Wait, can't I see this here? Yes. Yes. All right. Hello, everybody. Welcome to part 2 of getting like super nerdy with Bezier curves. We're gonna change it up a little bit from last time. Last time I tried to build this all live, which I don't know how interesting this was to watch for people, but I felt like I didn't really get very far because there's actually a lot of ground to cover, and yeah, we only got like 20% in, and it took 50 minutes or 45 minutes to get to that point. So I basically already built everything up, and I will walk you through. First of all, like I'm gonna recap on what we did last time, because I think I can just basically say this in about 5 minutes, and then you don't have to watch part 1. If you still want to watch me build those little algorithms here, then yeah, you can watch part 1. Other than that, or otherwise, just don't bother. Because I think it was a little drawn out. In any case, it's already getting a little drawn out here in the beginning, so let's just get into it. So first I want to talk about the Casteljau algorithms, which are basically just linear interpolations, like I already explained last time. So say we have those 2 points, then we can interpolate linearly in between, which gives us a bunch of points here in between. But for linear Bezier curve, which that basically is, we only need to connect those 2 points and we get a line in between. So yeah, this is linear Bezier curve. Oh yeah, and by the way, I'm gonna have all those files downloadable in the description, but I think this is even maybe interesting for people that aren't really into Grasshopper. Yeah, we're talking about this because curvature alignment, which is kind of the topic, and we will get there. But curvature alignment is what we do in automotive industry. We try to align curves and surfaces to each other to generate like smooth organic shapes, and the software that we use, they kind of provide curvature alignment for us. Grasshopper doesn't, so if we want to use Grasshopper in like an automotive environment, it might be useful to have a way of constructing curvature alignment. So yeah, let's just continue. Let's say we have 3 points. Then we can also connect them again with like points in between. Let's turn them down a little bit. So what we're basically doing, we're connecting those points with lines, and then we divide those lines up with points. And if we just do this, we can now have 2 points, basically 1 point on this line, 1 point on that line, and they move between 0 and 1, which is basically the so-called, I mean, it's always referred in Grasshopper as a t value. Might be time, I don't know. Anyway, t. Yeah, this gives a position from 0 to 1 between those 2 points, or 3 points. So now we can connect those 2 points up again, like this. And then we can put a point on that curve, which is basically getting the same input as those 2 points. So it's again from 0 to 1. So that would be this point. And now if we follow the yellow point, this would describe our Bezier curve, which if we plug in multiple curves or multiple values from 0 to 1, then it describes here our Bezier curve. And I guess we can hide all those points and maybe hide those too. Let's keep those. They actually good to see. So now we have a curve here in between. Those are in alias what we call hulls. Now we can move those points around, and we have here our quadratic Bezier curve. So next step would be a cubic Bezier curve. So let's hide this and turn those points on. So now we have 4 points, and stuff is actually getting interesting. So we can, let's do the same thing again. So those points, they are kind of connected like this. So we kind of expect this to get an S shape in between. And then we interpolate in between those points again. So we have now those 3 points that we can connect again with lines. Now we put points on those lines again. And then you might already have figured out what the next step is, which is just a connection between those points. Now we have another line, and then again we put a point on that line, and now this point describes our cubic Bezier curve. So let's plug in like a bunch of values, hide all those points. And now here we see have our cubic Bezier curve, and again, if we move those points around, this curve kind of follows. And that way we can actually control smooth curves in space. So this is all fine and dandy, but you can already see we here depending on how many points we have, we actually need to repeat those operations over and over again, which is kind of annoying because now we have to know how many points we have beforehand. So this is not a universal algorithm. This can really only construct cubic Bezier curves. If we want to construct any Bezier curve, then we have to put this in a loop. So that's what I did here. Let's turn this one on and this one off. So this is the same curve now. Maybe make this a little thicker. So this is now the same curve, with the difference that we only need this element here once, and we put this in between those anemone loops, or 2 nodes that basically build a loop. So here the data flows actually backwards, and then here we just count the amount of points, feed this in. This tells the algorithm how many times it should repeat. The downside with this, at least in Grasshopper, is that, as you can see, this is now very janky because Grasshopper doesn't like when data runs backwards and has to recalculate. So this is not really good in Grasshopper to do it that way. And as far as I understand, it's also in general, I think, not the most efficient way of calculating your Bezier curve. I think it's the numerically most stable way of doing it. But as I understand, it doesn't really matter unless you get like to something like degree 20 curves or so. That there is actually a downside using another method, which I'm going to show you now. So yeah, for like alias, for example, where we only have 9-degree curves, it doesn't matter. Like we don't have to use the numerically more stable algorithm. So the next algorithm that we use is based on Bernstein polynomials. So let me show you real quick what those are. So let's say we have graphs. Oops. Here we are. So let's say, okay, actually, let's start a little bit earlier. So let's say we have 4 points again, and this time they are connected like this, right? So, and we can say every one of those curves has a graph assigned to it. And when I move my points again from in the domain of the curve from 0 to 1, basically the t value, then this is what we have at the bottom here. This represents our t value, and then we get another value back here, right? So we put a t value in, let's say 0.2 or 0.2, and then we draw up here. So for the red curve, this would give us almost a 0.4. For the blue curve, it gives us a little bit below 0.2. For the orange curve, it's almost 0, and for the blue curve, do we already? Oh yeah, here the purple curve, it's a little bit above 4. So those are values that we get back, and with those values, let's say let's actually turn on the curve that we know we're talking about, and also I'm gonna turn on the point on the curve, which is now here at 0, basically, and then we also turn on those points. So now here, when this point sits at 0, you can see this point here gets like a 1 value, which means it has the most influence, or it has the only influence. The only influence here is by that point, right? And then if we move this point, then you can see that those points here, they're also moving, right? And it basically tells you, okay, here on this position, those points, they have different values, different amounts of influence. They always add up to 1, right? And then when we go all the way to the end, then it's only this orange point that has influence on the curve here in this position, and all the other points have 0 influence. So, and we can actually use this information, and yeah, those polynomials, they are fixed. So it always depends on how many points you have. Let's just say we change the amount of points. We're not going to change them here. You will only, let's just zoom in here. Let's just say we have, for example, 7 points here. Then we get 7 graphs out of it. Actually, why not connect this here too? And then that also means that we get 7 values depending on how many points we have. And the more points, the more of those curves we get, right? So now this is a linear. This would represent a linear Bezier curve, and you can see like the influence of the points. They just basically cross over here in the middle, and then yeah, this basically what a linear Bezier curve with Bernstein polynomials would look like. And then as soon as we have more points, then yeah, the ratio is a little bit more complex. I mean, so it could go into how they are calculated. Maybe, yeah, maybe I do this real quick. So yeah, I just basically try to copy this little equation here in on Wikipedia, and let me zoom into this a little bit. Yeah, so it's basically it's only this that is interesting. This will generate your polynomials. So here this is a so-called binomial coefficient. So it kind of gives you out those rows of numbers. So if you basically have we can actually do this here. So if we have let's say we go to 1 degree, now you see we have here we get the number 1 and 1 out. This is basically would be this row. Now if we go to 2 degrees, then we have 1, 2, 1. If we go to 3 degrees, we get 1, 3, 3, 1, and so on and so forth. So 5 is the bottom row here is like 1, 5, 10, 10, 5, 1. Yeah, and this is basically what's happening here. Then I feed this into the little equation here, and that gives out basically a number of graphs, and those are my Bernstein polynomials. So yeah, I think enough about that. So let's go back to the cubic Bezier curve, and let's say, yeah, exactly. So we have all those values now, and we basically, with help of those values, we can now describe where this point sits, and what we need for that is any point. So right now this is just the average of those 4 CVs here, but it doesn't need to be. So this point can be anywhere. And then from this point on, we can imagine we draw vectors out. Vectors to our CVs, to our control vertices. And now this value, that we get out of here will basically, wait a second, why is this? Why is only 1, 2? Because they're just sitting on top of each other. My God. Let's move this a little bit. Yeah. Now we have 4 points. My brain just didn't like that. Okay, so we draw those vectors, and the number we get out is basically telling us how long this vector is. So from this point to that CV, that would be a vector of 1, right? And now if this, let's say here, this blue point, it would only be at around 0.2. So the vector that we actually see for this point here, that would be much shorter. So can actually, now let's turn those off, and then those are the actual vectors. So now you can see this is only a 0.2 long vector. This is even shorter. According to this, is almost 0. This is a little longer, and yeah. And this actually, yeah, this is always from 0 to 1. So this looks now that as if this vector is as long as that one, but it's only because this point is also closer here than this one is here. So now to actually draw out this point, all we have to do is we have to add up those vectors, which we can actually do by just putting them one after another. And you can see now those vectors are going to point at this point here on the curve. And when I move this around, the vector changes according to the value that we get from here. And it draws out our Bezier curve. And what's really nice about this is that it is quite stable. Let's turn this off, turn this on. So this is very stable. So I told you I can just move this point here around, right? So let's just internalize the data here. Click on this point. So if we move this point, it doesn't matter, it just draws different vectors, but they always end up here in this point when we add them up. So now if I move this around, see, it's the same principle. Doesn't matter where this point sits from where you draw the vectors. So now we got this back. Point is back here. So yeah, as I said, what's really nice about this is now it doesn't matter how many points I feed in. This will always just calculate it. So we don't have the same problem as with this solution here. And we also don't run in loops, right? These are just equations that are calculated, and then I get a certain value out of it, and we just add those values up, and yeah, we get those. We get this point. And then if we do this for not just one value, but let's say we have like 100 values from 0 to 1, then it will draw out the curve for us, which basically happens here, right? And yeah, if I start moving those points around here, see, this is not as janky as as the other algorithm that we had. The actual way of how this would be calculated, I think in the background, is matrix based, but it is like it takes the Bernstein polynomials as a basis, just translated into matrix. So, for example, for a degree 3 curve, which is this now. So this again, you see this. Highlight this a little bit. So you see this point running around the same curve, right? But it's not using this curve to kind of decide where the point is. It's using this matrix calculation, which basically just means you have your amount of points. So you basically have no, sorry. So this is the t value. This gets split up into like multiple rows, depending on how many points you have. And then you calculate this with a fixed matrix. So this would be for degree 3. This would be the matrix for degree 2 curve. And this is fixed the same way as those polynomials, or those graphs here. The polynomials are fixed. And then they just get multiplied with x, y, and z values of like 4 points here and 3 points here. And that, yeah, gives out, so because this is, you see, this has nothing to do with this curve here right now. It's just another example of a degree 2 curve. I just wanted to put it there to kind of show what the difference would be between degree 2 and degree 3. And you can actually set this up in a similar way as we did this algorithm here, where actually everything gets calculated and it doesn't matter how many points you feed in. I just don't know how to do this, so that's why I kind of stopped it here. So, and this is very efficient. The computers really like matrix calculation. Actually, I might link a number file, or was it computer file? I don't know. A really interesting little explanation of how matrix calculations are used in computer graphics for transformations, rotations, all this kind of stuff, because it's just super efficient for computers to calculate. All right, so matrix, okay. So the next step is, now that we actually have our curve, we can turn this all off. So we have our curve, and we can actually run a point along this curve. And for curvature alignment, or also tangent alignment, we like to evaluate the curve and figure out what actually the tangent direction is, to be able to compare this to tangent direction of another curve and get them aligned. So the way to do this is actually, it's so simple. Like when I heard about this the first time, I couldn't actually believe how easy that is. So we generate 2 points, and do those 2 points. They basically generate a vector. Right now this is just a unit vector that is scaled up, so the vector size doesn't change, but it's basically just a connection from this point to that point. And we only want the direction, so it doesn't matter really to us how long this vector is. So and then if we now that we have those 2 points, we can just bring them together really closely, and then if they're super close, you can see here it's like 0.00000001 millimeters or units. Then that means that this is basically those 2 points sit on top of each other, but not just quite. So, but yeah, this is within tolerances. This is like close enough for us to evaluate the vector. And now when we, let's say, move this point around, you can see how the direction here is always pointing in the direction of the curve, which would be the tangent direction. So that's one thing that we want to evaluate. Another one is the curvature, which can be done by pretty much using the same principle, but instead of 1 point, instead of 1 extra point, we have 2 extra points. And now we can build a circle through those 3 points, and this circle basically describes the curvature on that position. But again, only if we get those points really closely together. So now, and actually make this curve a little more interesting. Let's bring this down here. So now if we slide this point around the curve and evaluate the curvature, you can see our circle changes. And the radius of the circle, this is basically what the curvature is. And then if we bring 2 curves together and we want them to transition curvature into each other, the only thing that means that where those 2 curves meet, those circles would be the same size basically, right? So because they have the same curvature, the same radius in this position. And tangent would mean that they have the same tangent direction, which is basically the vector that we were just looking at. Okay, so this is all the basics about Bezier curves. I mean, yeah, there's probably much more to know, and I will link 2 videos in the description. One is this one by what's that? Coding Train, I think is the name. The Coding Train, which is super entertaining. This guy is like very animated, and he kind of walks you through Bezier curves, probably explains everything I just explained to you much better, and goes into other stuff that I don't really find that I mean, it is interesting, just not that oops, let's put it here. Just never answered my question of how to transition 2 curves curvature into each other. And then another really great video is here by Freya Homer. I don't know how to pronounce his name, but the beauty of Bezier curves, really worth a watch. It's done very nice, very well graphically and everything. It's very appealing to the eye, let's put it that way. But yeah, there are going to be links in the description if you guys want to like see somebody explain this a little bit better than me. So, okay, now let's get into the meat of this whole presentation. So, let's say you have 2 curves. They are kind of sitting next to each other in space, and you want to tell this curve that it should run curvature out of that curve. How would you do this? So, first we start with a position alignment, which basically just means we move this point here. So the only thing we need to figure out is what is this vector from that point to that point, and then move this point along the vector until the end. So this would be basically the position move, super straightforward. So the next one is tangent, which is, just as easy to understand. You just need to basically connect this point with that point with a line and then extend it. And somewhere on this line, this point here has to sit. And it doesn't really matter where exactly, as long as you have it in like on the same trajectory. Those 2 curves will kind of transition tangent into each other. So let's move this point here, and then we can actually slide this point around back and forth, and it doesn't matter. Like wherever, as long as this point sits on the same line, this will be a smooth transition, relatively speaking, smooth transition. Actually, let's turn on the graphs. So and let's bring this back again and go here to 0. Yes. So Now, if you put on curvature plots on your curves, you can see now those two plots, they kind of meet here in a point. So this means this is a tangent. This is a position connection. Now, if you wanna get this tangent, then you see what happens is this graph basically folds over, and those graphs, those curvature plots, they sit now like they meet each other, but this point and that point, they are not in the same position. This is basically what needs to happen if you have curvature alignment. So now we have to move this point, and this curvature plot will come down here. Like this point of the curvature plot will come down here. And then if we actually get like a really smooth transition from this curvature plot into this curvature plot, that means that we have a G3 connection, which is one step beyond curvature. But we're not gonna get into this really, because I have no idea how that works. It would be in calculus. It would be the third derivative, I think. But yeah, I have no idea about calculus. So, all right, let's hide this. Let's hide this plot again. So how do we figure out where this point needs to sit? So, actually, I'm gonna hide those this curve here for the moment, because I kind of want to draw something out and explain to you how we calculate this other point. So let's just turn this on and that on, and actually, so now you see this is again the Bezier curve that we described before, and when I move this point around on that curve, that basically means that those points, they move around here on those lines, right? So this is kind of how we can evaluate the position on that curve, or how this curve is constructed with the Casteljau algorithm. I hope I'm pronouncing this correctly. So let's just do a real quick screenshot of this. Wait, where's my mouse? Oh yeah, here. So let's grab this and save this here. Yes. Close this, and then now where did I want to go? I wanted to get this here. Yes. So let's let's open this in Paint 3D. Yay. We're using Paint. Okay. So let's say, I mean, this is just one Bezier curve, but we could also imagine that this curve is split right here, and we actually have two Bezier curves. And maybe we just get rid of this here real quick. So we could say, okay, those are two Bezier curves, and they, like this here, oops, is one, this here is the other, and then they have like 1 point here, 1 point here, 1 point here. The other one has 1 point here, 1 point here, and 1 point here. And we already know where the position point is, right? We did this alignment, and we also aligned the tangent point. So the only point that we need to figure out is this point over there. This is our curvature point. And if we now go back, we have another point here that kind of floats in space between those two curves. And if we can figure out where this point sits, then we can figure out where that point sits. So the way we would do this is, okay, let's say we have a vector from here to here. We know the length of this and direction of this vector. This would be our vector A. Let's do it, I guess, A. And then we have another vector from here to here, but this here is still a question mark. But we could call this our vector B for now. Then another thing we know is that, or actually, I have to track back a little bit. Let's go back. So, when we construct a Bezier curve, and let's just say, okay, this is one Bezier curve, then we know that this from here to here, this is basically 0 and 1, right? And from here to here, this is also 0 and 1, and from here to here, this is also 0 to 1, and we move points along those lines between 0 and 1, and this point, where those points sit in relationship, is always the same. So this is, let's just say these are 2/3, and this is 1/3, and then the same is true for this. This is 2/3, and this is 1/3. So I guess you get it. The ratios are always the same. So now if we say this is A, vector A, and this is B, then we could call this here, just say C, and we call this here D, and then here this one we call little e, and this one we call little f. So, or actually, let's make this a different color. Let's make them blue. So this one is E. Oops, drawing with a mouse is not so easy. It's also ugly. This one also ugly, but we leave it. And then this would be F. So we basically know that if like that, this ratio is the same as this ratio, and this ratio is also the same as this ratio. So we could say B divided by A equals little e, oops, wrong color, E divided by F. And then if we actually want, because this is a given, this is given, we want to figure out B. So we can just multiply everything by A. So then that means B would be equals A times E divided by F. So now what we basically did, we figured out the length of this vector, of the vector B, and we know the direction because the direction is basically the A vector direction. So we multiply A, the direction, by E divided by F, and then we get the B vector, and we can just put this vector here on this point, the point we also know, and then we get this point here. So this basically calculates that point. And now since we have this point, we know what C is, so we can do the same thing again. We just have D divided by C, and that equals, E divided by F again. So you can already see where this is going. We multiply everything by C. That means D equals C times E divided by F. And that would be this point here. So now this is the equation for that point, or equation, I don't know. This is very, very simple math. So let's save this. Save. Okay. Let's call this capture 2. Close this and actually bring this in pure F. So, so we have this here. Now let's hide this and let's get back to our actual situation with our curve aligned. Okay, so now let's put this here. So now we've done the position alignment here. We've done the tangent alignment here. And now the next thing we need to do is the curvature alignment. So first we have to figure out this point here, which would be here. Actually, here what I'm doing, I'm getting the E divided by F, right? This is the distance between those 2 points and the distance between those 2 points divided. So this distance divided by that distance comes here. And then I multiply this here with the vector A, which is the vector from here to here. I just multiply this. And then I move this point here by the multiplied vector, which basically brings this point somewhere over here. Let's see where this ends up. Oh yeah, here. So this is now basically our point over here. And then we do the same thing again. We already know the F divided by E. Let's hide this all. Oops. Or actually leave this one. So now we get this length and multiply it by this ratio, and then we get another point that is here, and this would be this point now. And if we move this point over here, and actually now let's watch the curvature plot while we do this. So this point moves, and we see we have a very smooth curvature plot. So the reason this is so super smooth is because this is G3, 4, 5, 6, like infinite. This is as if that all was one curve, because remember, we basically found this point where this point would be if this was one curve. So that's why this looks like one curve. Now we can actually move this point to other positions. It doesn't have to be exactly there. It can actually move along the tangent axis, which I don't know why that is the case, but here, look at this, it actually works. So now you see that the curvature plot itself changes, but the position where they meet is the same. So that means we have curvature transition here. But you need to be careful with this, because you can still torture this curve to a point where they don't really quite work that well with each other anymore. But I mean, it's, for the most part, it's a pretty decent transition. And for class A reflective surfaces, where you can actually really see reflections on, then you want to go a little further than just to G2 or curvature transition. So yeah, this is pretty much how you can construct a curvature transition in Grasshopper. Almost. This really only works for quadratic Bezier curves. It does not work for curves with more degrees, because if we go back to this, you see how here when we look at the Bernstein polynomials, the more points we have, the more polynomials we get. That means the ratios, the amount of effect that the points have on the curve is gonna be different depending on how many points you have. You can already see, like, just watch this point here move, right? It will kind of, like, all those points kind of move in different positions. So that means we kind of have to put this into into our equation, into our algorithm, if we want to align curves that have more than just 2 degrees. So let's say we have a curve, and let's zoom to this curve. Let's say we have a curve. So I kind of put together a little starting. What are you? You're from here, yes. So I have put up just a little test environment where I can increase the amount of points of my curve without changing the starting positions, because I don't want to just put more points on the same curve. I just want to basically append another CV in the end, and then you can actually already here. Let's zoom in. Maybe this needs to be a little bigger. So now, if a little out that you can see actually the points adding. So the more points I add here at the bottom, you can see how the curvature of this curve here changes. And actually, let's just get a curvature evaluation thingy here. So I mean, we don't have to write this ourselves anymore. Grasshopper actually gives us wait, where? No. Wait, what is your issue? Import parameter failed. Why? This is a curve. Because we have to put a t value there. 1.0. That's why. Yes. So we bring this to 0. And now we have our radius here that describes the curvature of our Bezier curve. And if we change the degrees, you see how without changing this point, the curvature of the curve actually changes. So we have to account for this in our algorithm, which we do by, so so imagine, right? I'm figuring this out. I finally, it took me, I'm not even joking. It took me years to kind of understand how to get how to figure out this point here. And when it came to me, I was a little upset with myself that it took me really so long to see the curvature transition in the regular Bezier curve construction. So after a year of trying to read up on math and scour the internet for any explanation on this that I can understand, I finally figure it out. And then the next step is I realize it doesn't work when you have more CVs. So I cried a little bit, and then I started experimenting around, and I figured out the ratios. So the ratios are in a way that, like, the top number here describes the amount of points that I have. So if I have 2 points, I divide them by 2, and then this gives me a 1. If I have 3 points, I divide them by 4, that gives me 0.75, and then I multiply this, and then I divide this by 1 again for the lead ratio, and for the slave, for the curve that I align to it ratio, I just use that ratio, and I multiply the vector, like the amount I move the point by. I multiply this with the lead ratio and then the slave ratio, depending on how many points my curve has. Like if I here turn this curve on, right? This curve also has a certain amount of points, and I can, the same way as the other curve, I can change it. All right, so obviously I can just count the points and then calculate, and this is basically what I do here. I get this ratio, this is my lead ratio, and then here I have my slave ratio. I multiply those two with each other, and then I multiply, and here we basically have the have the same situation as here. I have my vector d, but I multiply it again by this ratio that I get out of here. Actually, let's see what that would be for those two curves. It would be 1.2. So the vector I had to move, I moved this point by, I multiply this vector by another 1.2. So, and this value will change every time I change the amount of points, right? And it can get like kind of a weird value sometimes. So, but yeah, so this is kind of what you need to keep in mind if you want to align curves to each other that are more than just 2 or 3 points. So, but here now let's just align this. So here we have position align again, so that works fine. Then here we have curvature tangent align, that works also fine. Then we can move this point here around, and here now we have curvature line, and then we can also move this point around. But yeah, so those two lines are now aligned curvature. Oh, two curves, sorry, are aligned curvature to each other. And yeah, depending on how many points I have here, you can see this point move, right? And then the same is true for the top one. If I move those, or if I increase the amount of CVs or reduce them, this point will move. So yeah, this is pretty much everything you need to know if you want to align two curves to each other. There is one more thing. Let's just talk about this real quick, because there is also a lot of times you don't just want to align. You might also wanna blend. Oops, what happened? Oh, okay. Oh, we're getting slow now. Yeah, I guess I kind of put too many groups in groups with this algorithm here. So in any case, let's make this visible. Okay. So, and I will just explain this real quick for position align, but this I'm basically reusing the same concept again and again. So I'm basically, like, you see here I have my position align, how we used it before, and now I'm just tagging this blend part at the end of it. So let's do the position align again, and then we tell the algorithm how many points we want to blend. And then in Alias, at least, we have something that they call blend factor. And this is basically, it's taking values from ratios, like depending on how many points I have, I get like a certain amount of ratios between 0 and 1. And then I just take them to the power of the blend factor. So if I put them at 1, this is usually what Alias does, then this point, the last point, gets moved 0.2, or let's say 20% of what the first point got moved. So yeah. So you see this point here, it still moves, but only 0.2, so 20%. Now if we have less blend points, you see how here the ratios change, and now this point basically stays in the same position. The next point gets moved just 25%. This point gets moved 50%, and so on and so forth. And then if we take this to a different factor, like if we take this to a factor of 10, for example, then those points almost don't move at all anymore. when you get into the negative, they kind of get like super out of hand and leave probably the atmosphere in this situation. But yeah, everything positive just basically gets you closer to the original position where they used to be. And then yeah, I basically have this for the tangent line too, and I put this behind the curvature line too. So this is basically what happens with the alias align tool. This is how the blend function in the alias align tool works. Yeah. Okay. Let's see how long did this take us? So I don't even know. But probably a little less than an hour. Oh yeah, I actually have no idea. Yeah, but this was basically all I wanted to explain. Maybe I get into how I could use this for surfaces, like this principle to align surfaces to each other, which, I mean, just as a little spoiler, you would imagine you have two surfaces. You can also break them down into multiple lines. Like if you align every row of CVs to each other, positional first, then you can align a tangent and curvature. So it's basically like aligning a bunch of curves to each other. But I can maybe show you next time how I would set this up. I definitely will upload those two, like those two files, those two Grasshopper files, and put a link in the description. So if you're like super nerdy, or you actually have a use case for alignment, you can pick them up. You can, like with this principle, you can also build a blend curve. Maybe. Let's see. I have to go through my files, because I kind of build a whole set of Bezier tools for Grasshopper. Maybe I put a file together so you guys can kind of check those out. They might not be all like super robust, so don't be too harsh on me, and don't rely too much on them in like a production environment. But maybe just to look under the hood and maybe get some inspiration on how to build those tools yourself. Yeah. All right. Yeah. Thanks for watching, and till next time. Bye.